this computer. So if you have any questions, you can stop me and we can discuss this. But the main topic for today would be electromagnetic induction and the Faraday law and the Lenz's law, which is responsible for the negative sign. So I can start maybe by some short review, or we can just say Faraday's law. Yeah. So I'm going to remind you a little bit how we derive it. So we have this Maxwell equation saying that gradient cross product with the electric field can be found or is equals to negative derivatives over time from the magnetic field. So the main point or the main meaning of this equation is that changing in time magnetic field can induce electric field. And if it's inside a conductor, then you have, as a result of the electric field, you will have the current. So we can integrate it over area. So let's say you have a loop like this, and you have magnetic field going through this loop, and somehow you can change this magnetic field. Maybe just magnetic field is changing in time, or loop is moving in space, and the magnetic field through the loop will change. So we can calculate the integral over the area of this loop. So this is the area. And this is what we can get. So an integral gradient electric field element of the area should be equal negative. I'm going to put derivatives over time out, and the integral magnetic field over the area. And this would be area of the loop. Now, the left side and the right side can be written in different terms. So the right side, we can introduce the flux of magnetic field through the loop. And we can say that this is a change in time or rate of the change in time of the flux of the magnetic field through the loop. So then we call this flux of magnetic field. The left side is a little bit more tricky. So we use what's called Ostrogradsky-Gauss theorem. And instead of integrating over area, we can start integrating over the contour of this loop. So let's say you have this contour, this is the loop itself, so gamma. So then this integral over area can be rewritten as an integral over the contour, gamma. And this would be the dot product between the electric field and the small element of this contour. And this contour is closed contour. So this is already looks nicer to us, but we can do even better job. So because electric field can be related to an electric potential, V. So because electric field can be equal negative gradient V, so we can plug this electric field here and we can integrate over this gamma, and the result will be very interesting. That will be change in the electric potential when you go along the loop. It's like if you write a loop rule, you always have a drop of potential across each element. Drop of potential across the battery, drop of potential across a resistance or a capacitor. This would be another contribution to this drop of potential. You can make this, you can make a interpretation of this as a drop of potential or just induced EMF due to changing in time flux of magnetic field. And this is what we call Faraday's law. That an EMF or drop of potential will be induced if you have flux of magnetic field changing in time through the loop. The only what I probably would add to this, I would say, if you have several turns, then I would probably modify this. I would say that each turn will contribute to your drop of potential, and you just have to multiply it by number of turns. Where n is the number of turns. Of course, if you have only one turn, then it's the same. So if n equal 1, that means you have a one loop and you can represent your induced EMF as a battery like this. But if you have more turns, like if n equal 2, then it's like you have two of them connected in series. So basically it's equivalent double EMF. And this kind of, I would say, obvious or very natural statement. Yeah, you have one turn, another turn, they connected in series. In each turn you will induce EMF, so they add together. So then the total EMF induced in the loop with many turns, I would just add this multiplier n, which corresponds to the number of turns. Okay, let's talk a little bit about flux of magnetic field, how to calculate it, what does it mean, and so on again. Then we can talk about the negative sign, because negative sign is a separate topic and it's interesting concept actually. It will tell me the direction of the induced EMF. And then we can solve as many examples as we in principle can. Do you have a question or it's all fine? So far so good, yeah? Okay, then we can do maybe subtopic flux of magnetic field. So the flux of magnetic field is the same as the flux of electric field. The only difference is that you have a dot product between element of area and the magnetic field. And if you remember, if you have certain area, delta S, you can find a vector which is normal to the area. Normal. And you have magnetic field. And you probably remember this or maybe not, but we can split this magnetic field into component perpendicular to the surface and parallel to the surface. So the parallel component is not going to contribute to the flux. This is a parallel component. We don't care about parallel component. It's like if you have a flow of fluids through a surface, you're interested in how much fluid is going through this surface. The parallel component does not contribute to this flux. Only the perpendicular component contributes. So elementary flux, the same as we did for the electric field. The elementary flux would be B area and cos theta, when angle theta is the angle between the normal and the magnetic field. But B cos theta, this is a component perpendicular to the loop or parallel to the vector n. B perpendicular area. So in this equation, B perpendicular is a component of the field perpendicular to the loop. or parallel to the vector n, because vector n is a normal vector. And ds, or it's a small area, so it's area. And then in the equation, it's a dot product. That's why I have cos theta. This is how we calculate magnitude. The sign plus or minus, it's relative. It depends what you call the normal, what direction you call positive or you call negative. There is no strict definition right now. So the sign is not that important, but the magnitude, something like this. And the units. Let's talk about units a little bit. Well, apparently units should be Tesla multiplied by meter square. And people call them Weber or just WB. 1 Weber is a relatively strong magnetic flux, so you can guess. So if you have a flux of 1 Weber, this means you have 1 Tesla of magnetic field going through the 1 meter square area. 1 Tesla is a strong field, plus you generate this field across 1 meter square area, so it's a huge flux. Maybe it's better to talk about milli or micro Weber instead of Webers. So it would be too strong for us. So then we can just maybe solve 1 or 2 examples how to calculate the flux, just to get idea what is this. But if you remember how we did it for electric field, this very close. So let's have a one example on this. Example. So let's say I have magnetic field from left to right. So this is a magnetic field, B. It would be hard for me to draw like a 3D picture. So my loop will be square loop, and the orientation of the loop would be like this. So this means magnetic field is going through the loop at angle, basically angle theta 0. So I can draw maybe what's called side view from this. Side view means, let's say I'm going to look at this situation from this direction. Then magnetic field will be coming towards me like this. So this would be the magnetic field. And the loop will look something like that. So these are the same image, but it's a side view. So when I look from on the first image, I see this only this side. And the direction of the field. I don't know if it makes sense or not, but otherwise I will have to draw like a three-dimensional picture like this. Or maybe it's not a bad idea. Yeah? So let's say we would like to find the flux of magnetic field, the magnitude through the loop. If, let's say, the area of this loop, let's say 10 centimeters by 10 centimeters, so it would be 0.1 and 0.1, 10 to negative 2 meter square, and magnetic field, well, let's say 20 millitesla. The important part would be the cos theta, the angle. How do you believe? What is the angle theta in this case?
I mean, isn't it parallel? So
The magnetic field is perpendicular to the loop. It's
Yeah,
parallel.
isn't
to,
it 90 degrees?
Aha. So it's a little bit confusing. So let's write it again. B area and cos theta. Angle theta is the angle between normal and the magnetic field. What is the angle between normal and magnetic field?
So Lila was right.
So it's 0. It's
Yeah.
parallel to vector n. There is another way to look at this. Another way to look at this equation is find the B perpendicular to the loop. My whole entire magnetic field is now perpendicular to the loop, so I don't have any parallel component. I don't need any cancellation or whatever. So I can say that my B perpendicular is just the total field. Okay, then I can just plug them. 20 millitesla multiplied by 10 to negative 2 meter square. Millitesla and meter square will give me milliweber. And 20 multiplied by 10 to negative 2, 1, 2, 0.2. Yeah? Does it make sense? We are not talking about positive or negative because it depends on the direction and direction of the normal. You don't have any preferences, left or right. So then let's just keep the magnitude. What if I slightly change the direction or orientation of this loop inside magnetic field? I'm gonna keep the first view. So what if my loop is directed this way? So vector n will be like this.
now it's perpendicular.
Yes, and angle theta in this case would be.
90.
And how much lines of magnetic field goes through the loop? What is the flux of magnetic field in this case?
0.
0. So there is no component of the field which is perpendicular to the loop. So you can talk either about angle or about the component of the field which is perpendicular, and in this case you don't have it, just 0. Or I can maybe tilt it, the loop, not by 90 degree, but some non-trivial angle. So the same picture, and then I'll try to tilt my loop maybe this way. So then vector n perpendicular to the loop will be this. And let's say that vector n makes angle with a vertical line. So if angle theta with a vertical line is 30 degrees, or maybe based on the picture, let's make it 60 degrees. What will be the flux of magnetic field in this case? What is angle theta which I have to plug in the equation for the flux? It should be angle between what and what?
Between B field and N,
Yeah, and what is this angle?
30.
30. So the angle which I'm looking for, it's angle between B and N. It's 30 degrees. What is given to me is the angle between normal and vertical line. Who cares about vertical lines? They're not really important. The direction of the field and the normal, this is what is important. Or we can talk about component of the field which is perpendicular to the loop. So if this is my magnetic field, I would like to find this component. So then what will be the flux in this case? So we can go with the main equation with cos theta, magnetic field, area, cos theta. But we should plug 30 degree, yeah? B multiplied by A, I guess it's 0.2 milliweber because it's from previous one. And cos theta is a cos of 30 degrees. Is it square root of 3 over 2?
Yeah.
Square root of 3 is maybe 1.7 or something like this over 2. I would guess 0.17 milliweber or something like this. Can you confirm?
Yeah, it's like that. 0.173.
173, yeah. 1 over 2 and 0.2 will simplify to 0.1, and square root of 3 is 1.7, yeah. Cool. Questions? So then we basically understand a little bit about what is the flux of the field. So then the right side of the Faraday's equation, the flux. You can roughly think about this flux as a number of lines of magnetic field which cross the area and perpendicular to this area. So, okay, number of lines crossing the area. If you can somehow change this flux in time, you will generate electric field and EMF, electromotive force, or difference in potential. How exactly you can change number of lines? How exactly you can change the flux? How we can change it? Flux of magnetic fields. Cos theta. Well, what is on the surface? We can definitely change the strength of the magnetic field, yes? The magnetic field can get stronger or weaker. We can change B. We can try to change the area. So if you have a loop, if you try to reshape this loop or make it larger or make it smaller, the area itself, even without changing the strength of magnetic field, just changing the area, you will change the flux. And also you can change the angle. By the way, when you change the angle, this is what you use in generators. When you have generators, you rotate loop by hands inside an external constant magnetic field, and by changing the angle, you're changing flux. That means you're generating EMF. But there is something less trivial. We can also change the number of turns if you reshape a more complicated loop. So you can also change the number of turns. But this is rare. Number of turns. So for example, if you have a loop inside magnetic field, let's say like this, and you have magnetic field, let's say right now the flux is 4 points, 4 dots inside. If I try to reshape this, so I can create 2 turns. In the same magnetic field. So I am changing number of turns from n equal 1 to n equal 2. So effectively it should somehow be important. So I would probably write a more general form for the induced EMF. This would be the change in the flux over time. A more general form would be, if you have number of turns, change number of turns multiplied by flux through 1 turn. But number of turns is not a continuous value, so it's not easy to work with number of turns because you cannot change continuously from 1 turn to 2 or 3 turns. It's more working for an average induced EMF, and when you have initial and the final condition, and then you just take the difference in the fluxes. We will solve an example on this later. But let's go back to the Faraday's law. We kind of understand what is a flux and how you can change it in time. The next stop is the negative sign. What does it mean, negative sign? Negative sign means the direction of induced EMF. So it's going to be like on these pictures. Negative plate, positive plate, or vice versa. Positive plate, negative plate. In what direction you induce EMF by changing the flux of the field. So this is something called Lenz's law. I believe it's Lenz's law, like this. Lenz's law is about the direction of the induced EMF, and it's more a particular case, or it's more general rule. This is called Lachatelier, and I probably cannot spell this, but it's something came from chemistry, and I believe he was French, Lachatelier. I don't know if you took chemistry courses, you may not remember this. So the Lachatelier principle means that if your system is in equilibrium, but Lachatelier were talking about chemical equilibrium, but we can formulate a more general statement. Any system in equilibrium, so you have equilibrium like this. If you try to remove your system from equilibrium, there would be force, which will try to bring it back to equilibrium. So in other words, system will try to stay in the equilibrium. It's not going to be easy for us to remove the system out of this equilibrium state. Everyone likes status quo. Everyone likes to have a predictable life. So you're already in equilibrium state. You're fine with what's going on. And then if you have external influence, and external influence will try to move you out, you will fight back. This is true for chemistry, this is true for physics, even for maybe psychology. it's a more general principle. So Lenz's law is basically the same. So when you try to induce EMF by changing flux of magnetic field, the system will fight back. So the direction of the induced EMF will be such that it will try to reduce the change of the flux. So I'll try to write it down. The direction of the induced EMF is such that this induced EMF is a response to the change in the flux. So this response should try at least eliminate this change in flux. So the direction of the induced EMF is such that it will try to reduce the change in the flux. The original change. Of magnetic field. Probably this doesn't tell you a lot, but the logic is the following. You're trying to change the flux. For example, you increase the strength of the magnetic field. Then you will induce EMF. This EMF will induce current, and this current will create its own magnetic field to compensate the initial change. So it's gonna fight back. It will try to come back to initial state. It may not be successful, so it will just try. So I would underline this. It doesn't mean that you can completely reduce it. Yeah.
So the idea is the flux wants to be constant.
Yeah.
Okay.
And it doesn't mean that it will be successful, but it will give you the direction. And then when we say reduce, this means against the change, and this negative sign in the Faraday's law, it's responsible for this direction, to reduce, to keep the flux constant. Thank you, Leila. So let's write it again. EMF equals negative number of turns, the derivative from the flux over time. So this negative sign is the direction. So this direction is against the change, the derivative. So if my flux is increasing, the derivative is positive, then the EMF will be negative in a sense. And usually it's confusing. Even it sounds simple enough, in reality it takes a little bit of time to get used to the idea. What does it mean against? How you can keep your flux constant so you're still at the same equilibrium state. And let's have an example for this. So another example. So let's say I have magnetic field either into the page or out of the page. Let's say into the page. Okay, it will take some time for me to draw this picture like 5 times. Be patient with me. So let's say this is time equals 0. This is my loop. Let's make it a little bit larger. So This is going to be the loop. And loop is moving to the left in the direction of the magnetic field. So where we don't have crosses, that means there is no magnetic field. This is the only area with the magnetic field. And this is my loop. And this is time equals 0. For the flux of magnetic field, let's just count how many lines of magnetic field goes through the loop. So in this case, the flux of magnetic field would be 0. Yeah, because there are no any points, any lines crossing the loop. This is fine. I would like to wait a little bit of time. I will let my loop to move to the left. So this means I have to redraw this. I hope it's not going to be too boring because I have to do this several times, but we will see. Let's say my loop became maybe move closer. This is time equal 1. What is a new flux of the field?
Still 0.
It's still 0. What is the change of the flux? The change of the flux is the final flux minus initial. What will be the change?
Still 0.
Still 0. And induced EMF?
Zero as well.
Yeah, because we don't have any change, yes? Okay, I'll try to use this low part of this whiteboard. Probably I can fit 2 more pictures like this. Now will be more interesting part. The loop will start entering this area of the magnetic field, and we will see what will be the result of this motion of the loop. Look, I don't really change the magnetic field. I don't actually change the area, but the flux will change because loop partially will be inside magnetic field right now. Let's call this time equal 3 seconds or whatever. What is the flux of magnetic field right now?
2 or
2, yeah, I would say 2 is enough. And the direction of this flux is into the page, yes, whatever. Let's call this positive, for example. What is the change in the flux?
2.
2 minus 0, 2. I have a non-trivial change in the flux, yeah? And this change happened from time equal 1 to time equal 2. Sorry. This change happened from t equal 1 to t equal 2. So the time is delta t is 1, delta flux is 2. So we should have induced EMF. Now, what will be the direction of this induced EMF? This is the most important question. The induced EMF can be like this, for example, which will produce me a counterclockwise current, or maybe opposite, like this, clockwise current. So the direction of the induced EMF will be defined by the Lenz's law, by this negative sign. The rule is the following. The induced EMF will produce me current. Current will induce me magnetic field internal due to the current. And this magnetic field will try to come back to the status quo to reduce the change in the flux. How I would do this myself? What is the change? I get 2 more crosses here in the loop. How can I reduce it?
Adding 2 more, but going towards us.
Yeah. This would be induced field, which will try to eliminate the change. I'm focusing on the change. I got two more crosses, two lines of magnetic field going into the page. If I want to reduce it, I'm going to try to create magnetic field which will go out to cancel out this field. This will be magnetic field induced, not external, but induced magnetic field. What should be the current in the loop to produce magnetic field like this? What should be the direction of the current? We had this right-hand rule for when you have a loop, remember, and then the magnetic field at the center of this loop. If induced field is going towards me, then the direction of the current should be
To the left.
clockwise or counterclockwise?
Counterclockwise.
Counterclockwise. So this would be induced current. Yeah. And what will be the direction of the EMF, this induced EMF? The same, yeah? Like this. One more time. This direction of the EMF will induce me or produce counterclockwise current. The counterclockwise current, the induced current, will produce me magnetic field out of the page. And this extra magnetic field will try to compensate the change in the flux. It may not be able to compensate this completely, but it will try. So we are talking about the direction. So then I have EMF, which is going to be counterclockwise. So this is something usually hard to understand. You need to really work with this for a while to get used to the idea of the direction of this, of the Lenz's law, basically. Okay, let's move it a bit further. Let's say my loop will continue to move to the left. So next time, so let's say the loop will be somewhere here. And it will continue to move. What will be the flux right now?
4.
Flux 4. The change in the flux? By the
2.
change, I mean previous and this one, 2, yes, 2. And what will be the direction of the induced EMF? Clockwise or counterclockwise? What will be the direction of the induced current?
The same, counterclockwise.
The same. Why the same?
Because the induced the magnetic field has to go towards us on the opposite direction.
Because we look for the change. What is the change? Instead of 2 crosses, we got 4 crosses. Yes, we increased magnetic field which goes into the page. We want to fight against it. Beautiful. So then it's going to be counterclockwise. It would be cool if we can find force on the loop due to magnetic field. Let's look at this diagram for time equal 2. You have 4 segments. The one segment is vertical inside the magnetic field. The another vertical segment is outside of the magnetic field, and you have 2 horizontal segments. 2 horizontal segments are not important because the force would be down and up. It will try to squeeze the loop. But the left and right side, these are important. What will be the direction of the force on this left segment? You have current, you have magnetic field. It's a right-hand rule number 1. 4 fingers along magnetic field and thumb is along the current. To the left or to the right?
To the right.
To the right. Nice. What about force on the right segment? The direction of the force?
To the left.
No?
Well, the field, the current.
It's a tricky question. There is a trick.
It
Why
will
is it
start to
right? Because
rotate, right?
it's-
Because of it will create a torque. Or no?
To have a torque on the loop, you
Oh,
must have a component parallel to the loop.
Okay.
Lewis?
is it right or there's no force because there's no
Linka.
magnetic field on that side?
Exactly. The left side is moving inside magnetic field. The right side is moving in the area without magnetic field. So the net force will be to the right. This is magnetic friction. Remember, when you move something in magnetic field, there is a force opposite to the motion. And this is very important. So the force will be always opposite to the change in the flux or to the motion. So if you move your loop inside magnetic field, the force will push it back. Okay, let's move on. Let's have another time moment. When loop is inside magnetic field, I'm gonna make one more or maybe 2 more pictures on this. Let's say what's going on is something like that. We continue motion. So let's say now my loop is somewhere here. And it will continue to move further. So it's time equal 4. What is the flux of magnetic field right now?
4.
4. Can you tell me what will be the direction of the current or induced current in now? I can show you the previous pictures.
Counterclock?
So this was how before, and now counterclockwise, maybe, yeah? Leila, is it counterclockwise or clockwise? Or it's hard to say? Okay, let me help you. It's not counterclockwise. Lewis?
Wait, I'm thinking.
Okay.
Well, if it's not counter, it's clockwise.
No.
But isn't it going in the same direction? Like, what did it change from the last one to this one?
That was before. And this is now. What is the direction of the induced current or induced EMF?
Is
Well,
it have to be with the difference on flux?
yeah. What is the difference in the flux?
0.
0.
So there's no EMF.
There is no EMF. It was tricky. If loop is just moving inside magnetic field, uniform magnetic field, there is no change in the flux, yeah? That was 4 crosses before, now it's still 4 crosses and it will be 4 crosses. The flux does not change. So when loop is just moving inside magnetic field, there is no induced EMF because there is no change. When loop just enters this region of magnetic field from empty to magnetic field, there is a change. Only the change induced EMF. When you just simply move inside magnetic field, nothing really happens from flux point of view.
So it's just when there is like perturbation or whatever you want to
Yeah,
call it.
exactly. You have to try to change the current state, and only in this case you have response of the system.
Okay.
So probably this is going to be the last picture for me. So let's wait another 1 second. So now the loop will continue to move, and in this case it will try to move out from this region. So the loop is now somewhere here. T equal 5. What is the flux right now?
2.
2. So what is the change in the flux?
2.
Minus 2?
Yeah,
Yeah.
negative 2, because we lost 2 crosses. Now the most important part, the direction of the induced EMF.
I would say clockwise.
Clockwise. Okay, what should be the direction of the induced magnetic field? Let's go back from this, induced magnetic field. What is the change? What's happened? We lost 2 crosses, yes? How can we compensate on this?
Adding 2.
We want to add crosses, yes?
Yeah.
And this would be induced field. What should be the current, the direction of the current to have induced field into the page?
To the right,
You mean clockwise or counterclockwise?
clockwise.
Yeah,
Clockwise. So then this is the direction of your EMF. What will be the force? Can you guess? What will be the direction of the force on this right segment, right side segment? We can hear you.
I was thinking, but it's going in.
No, don't calculate it. Guess.
To
It's
the
like
right.
to the right, to the right. Why?
It's fighting back.
Fighting back, because you try to remove this from magnetic field. It will bring it back. Now we can use right-hand rule. Magnetic field is into the page, the current is down. So the force will be to the right. It's accurate. And the force on the left side segment is 0 because it's not inside magnetic field. So the only perturbation, only something happens when you try to change the flux. And yes, this is the Lenz's law. This is the direction of the EMF, positive or negative, or whatever.
so when it's entering, it goes opposite. But
The-
when it's going out, it tries to compensate.
The force is always opposite to velocity, and this what makes it friction-like force. That's why we can call this magnetic friction, because friction is always opposite to motion. So if you move your block on the surface to the left, the force will be to the right, and vice versa. The same happens here. And you can call this magnetic friction. Of course, magnetic friction depends on the current, and current depends on the resistance of this loop. let's say if it's a plastic loop, then there is infinite resistance, there will be no current. Even if you have induced EMF, there's not going to be any force because there is no current, there is no magnetic force. If it's a copper or aluminum loops, they have different resistance, the currents will be different, so the force will be different. Remember the demonstration, you have this copper, aluminum, and plastic rods. The strengths of the currents are different for them. Okay, that was my best explanation to what we can call this negative sign, the Lenz's law. So negative sign here. Well, now you know everything. You know how to calculate flux. We can just consider different situation when flux changing in time. And you know what is the direction of this induced EMF because we know Lenz's law. And you can get EMF, induced EMF, you can get magnitude and the direction for this induced EMF. So now we can start more serious examples. Questions maybe? You all good? You ready for examples?
Yeah.
More examples. Example A. So we can start with something simple. Let's say I'm going to change magnetic field just by myself. So B field, let's say increases from 0.1 Tesla to 0.2 Tesla in 3 seconds. Find average EMF. Find EMF average in the following loop. So let's say you have magnetic field out of the page. So in this case, I'm going to change the strength of the magnetic field only. I'm not going to change number of turns or angle or area. And I have, let's say, a square loop. This is my loop. And let's say the size of the loop A by A. So it's a square loop. So the size of this loop is 20 centimeters. So the loop is perpendicular to the magnetic field, so I don't have to care about cos theta because it's already perpendicular, meaning the cos equal to 1, theta equal to 0. I'm just having this loop inside magnetic field, and magnetic field is increasing. It's important. So we're going to increase the value of this magnetic field from 0.1 to 0.2 Tesla in 3 seconds. What will be average induced EMF in this case? Let's find it. We can do estimation, like we can find initial flux and the final flux, take the change in the flux divided by the time. That would be the rate. Because this is one term, maybe we don't have to put n in this. And we can forget about negative sign because the direction is a separate story. But we can start with the direction. What will be the direction, by the way? What should be the direction of the induced magnetic field?
Should be in.
in. Why?
Because this is out, so it's fighting.
And it's not only out, it's also increasing.
Mm.
If external field is out and decreasing, then I would like to support it, yes, and I would like to create magnetic field out to compensate the drop. In this case, magnetic field is increasing. You start to have a stronger field. So the induced field be induced will be in. It's very important. And then what will be the direction of the current or direction of the EMF? Clockwise or counterclockwise?
Clockwise.
Clockwise. Must be clockwise. Let's estimate the magnitude of this. So for the magnitude, I don't want to care about the sign. So delta flux and I can say something like flux final minus flux initial. We can just find the initial and the final flux and that's it. Okay, so let's say my flux initial. What equation would you use? I guess cos theta is equal to 1, yes, so it's just a magnetic field initial multiplied by area. So initial field is what? 0.1 Tesla. And area is 0.2 multiplied by 0.2, 0.04 meter square. Is it 4 milliweber? Yeah. What will be the final flux? The final flux means when your magnetic field has increased already.
Double that?
Yeah, just double this. Final magnetic field area 0.2 Tesla. The same value for the area. So 8 milliweber. So then I can plug this in. I can have change in the flux in the numerator and time of the change. And this happened in 3 seconds for me. So then the induced EMF would be change in the flux over time. So 8 minus 4.
Sorry, is it 0.04 or shouldn't be
It's-
0.4?
I put milli, no?
Oh, okay, okay.
1, 2, 3. So I have this 10 to negative 3. Yeah. Yeah, you're right. So 8 minus 4 is 4. 4 over 3, is it 1.3333, yeah? 1.33 millivolt. Webers over second should give me volts. So milliweber over second is millivolt. And the direction of this clockwise. We solve the problem. So you have a loop inside magnetic field, you start to increase the strength of the field, and you will generate EMF, average EMF for these 3 seconds, which will be 1.33 millivolts. And you know the direction. The direction probably is most challenging here. We can do the same problem with a little bit different setup if you want. A.2. All the same, but my magnetic field, let's say, equals to let me write a function for you. So some initial value 0.5 Tesla plus, I'm going to increase the strength 0.1 Tesla per second multiplied by time. So I'm increasing magnetic field with time. Yeah. Let's make it quadratic function. That will be more interesting. So I'm going to increase magnetic field in time as a parabola, as a quadratic function of time. So, and magnetic field is out of the page. The loop is the same. Can you find induced EMF? Now it's not average anymore, just induced EMF. But this is very similar to previous one. Yes, I'm increasing magnetic field is out, and it's getting stronger and stronger and stronger.
It should be the negative derivatives, right?
Yeah, it should be negative derivatives, but derivatives from the flux. What is the flux of magnetic field? Can I just say magnetic field as a function of time multiplied by area?
Yeah.
So then when I take derivatives from this, I can take derivatives only from magnetic field.
Yeah, that will be 0.2.
This will be only this part. Yeah, yeah, you're right. Factor 2 will go out. So if angle theta is constant and area is constant, only what is changing is the magnetic field itself. Then we can write this equation. EMF equals negative dB over dt and area and cos theta. So basically, when we take derivatives from the flux, we have to take derivatives only from the field, because area, we assume, stays the same and the cos theta is the same. And the direction would be defined by the same way. I have magnetic field out, increasing. It means that induced field should be into the page and EMF should be clockwise, no matter what. Okay, can we get the value for this? What is the derivatives from the field over time?
Is 0.2. Oh, yeah.
Yeah, you're right, 0.2. But 0.2 multiplied by time, yes?
Yeah.
Then we have area and we have cos theta. So 0.2 multiplied by 0.04 time and 1. So my EMF will be a function of time, because the rate at which magnetic field changes is increasing. So the EMF will be greater and greater and greater. So this is a direction, which is clockwise. And this would be the magnitude. I would say, let me double check. So there's going to be 8 millivolt per second and time. I pick these units because when time is in seconds, I'm going to get volts for EMF. How do you like this answer? So this means your induced EMF will be stronger and stronger every second. So it will be stronger by 8 millivolt, increased by 8 millivolt for every extra second of time. Is it good?
Yeah.
So then I can give you the number for EMF because it's a function of time. If I specify what is EMF at certain time, like after 10 seconds, well, maybe after 10 seconds from the very beginning, it will be 80 millivolt clockwise. Yeah. But after 1 second from the beginning, it will be only 8 millivolts, not 80. After 5 seconds, it will be 40 millivolt. Questions? So if my magnetic field will be into the page, then the direction of this induced EMF will change to counterclockwise instead of clockwise. If my magnetic field will be decreasing, then again you will change the direction of EMF. Yeah. Okay, let's move on. Let's have one more example. Example B. Let's say you have a strong current I, and you have a small loop here. Small loop. The current I either increasing or decreasing. Because of this current, you have magnetic field through the loop. If my current is increasing, then the magnetic field, external magnetic field through the small loop will increase. So you will have change of the flux. And you will induce either clockwise current or counterclockwise current in the small loop. Let's try to answer these questions. Find the direction of the induced current in the small loop. Induced current in the small loop. If first case, current I is increasing. Okay, what would you say? The current I in the straight wire is increasing. Let's go by small steps. The external field due to current in this area, what is the direction? I believe it was what right hand draw. The second
In.
item.
Yeah.
In, yes, everyone agree? So the small loop will be inside this magnetic field due to the current. So the current is increasing, meaning that the magnetic field is increasing. So you're gonna generate an induced EMF and induced current in the small loop. What will be the direction? Clockwise or counterclockwise? You increase current, meaning that you increase external field. How can you fight back?
Counterclockwise.
to fight back, you want to create the induced field.
I mean, that's going about opposite way, so out.
It's going
So-
out, yeah. So then it's going to be counterclockwise, yeah? Counterclockwise. B. What if my current is decreasing?
And it's the opposite.
So opposite means
Clockwise.
clockwise. And how can we explain this? The external field is getting weaker. You're losing crosses, basically. You want to support it. You want to bring it back to the original state. So your induced field will be into the page. So it can be generated only by clockwise current. What if current is constant? Constant, but loop is moving either towards the current or away from current. So, but loop is moving. But loop is approaching the current. This means you want to locate it closer. But current doesn't change. Only loop is moving.
It will be at the first one.
At the first one. Because why?
It's increasing the magnetic field.
The magnetic field. The magnetic field is closer. When you move closer to the current, magnetic field is stronger. You also get stronger field, not because you increase current, but because you move closer. Then there's going to be counterclockwise. If you move away this loop, then the EMF will be clockwise. What if you move your loop parallel to the current? What if you move this loop in this direction? Parallel to the wire, to the constant current. What kind of EMF you generate? Clockwise or counterclockwise?
There is no change if it stays the same distance, so no EMF.
No induced EMF. Very nice. If I want to write an equation, for example, for case A, I would write it this way. I would say EMF negative d over dt, magnetic field and area. Area probably is constant, yes? And cos theta is 1 because angle is 90 degrees. So then let's say negative dB over dt multiplied by area. If it's a circular loop, maybe we can just use pi radius square. So this is the area. But it's not very important. The more important how we change the field. So magnetic field, if you remember, produced by a current would be equal mu naught over 2 pi current and then the distance multiplied by the area. And this would be, and then I have to take derivatives over time, yeah? From this. And this will be interesting because the loop must be small. So then you don't care where to calculate magnetic field. So if it's a small loop, you can roughly say that this is a distance between the current and the loop. And you don't really distinguish the left side of the loop or the right side of the loop. the loop is small enough so you can approximately just take this distance as a constant, not changing. Otherwise, it would be hard for you to calculate the flux. You will need to integrate the flux. And so we can put it approximate then. So then induced EMF would be equal negative mu naught 2 pi d, the rate at which you change current, and the area. This is for small loop. Again, what I did right now, I basically changed the current, and I have the rate at which current changes. So the change in current will produce me the magnetic field through the loop, which is changing. And this is the rate of change of the magnetic field multiplied by area as the change of the flux. Okay, questions? So these two examples, they were about changing magnetic field itself, yeah? The strength of magnetic field. We have other options. We can change the area of the loop. And we can change cos theta, like generators. Or we can change all of them at once. That could be more complicated. So let's talk about a situation when your magnetic field is constant, but you change in the area. This would be example C. Let's say you have a square loop, which you reshape to a circular loop inside a magnetic field. You just change the shape, meaning that you're going to change the area. Let's say size is 2 centimeters. Is reshaped into a circular loop. In 2 seconds while this inside a magnetic field. Perpendicular to Tesla magnetic field. So then let's say you have magnetic field again like this. And then you have a square loop. The size of the loop is A, the size of the square, which you're gonna reshape. So you change the shape of this loop. So you create a circle, perfect circle. So that the time of the transition or transformation from square to circle is 2 seconds. The magnetic field is 2 Tesla. For simplicity, magnetic field is perpendicular to the loop, so we don't have to deal with cos theta. I'm gonna just change the shape, meaning that I'm gonna change the area. Okay. And I do this in 2 seconds. How much induced EMF I will generate, and what will be the direction of this induced EMF? Is it going to be clockwise or counterclockwise? what you gonna do? What will be your steps?
I guess it's going to be clockwise because the area will decrease, so the B field induced in the loop will decrease. So
1 second, Lewis. The area will increase or decrease?
decrease.
Okay,
It's
let's
it's
say
from a
if area decreases, then it should be clockwise, yeah?
yeah, because it
But
want to
if area increases,
counterclockwise.
it will be counterclockwise. Can we compare area? When you
Yeah.
reshape a square like this, I understand what is the area of the square. It's a square, it's fine. But what will be the area of the resultant circle?
If you
After,
just reshape it, but like your circumference is the same as it, wouldn't it be the same area?
no, why? The circumference will be the same. Or
Oh.
the perimeter will be the same. Okay, we can find the radius of the circle, yes?
I think first we can find like the diameter of the square.
Yeah, because maybe I'm thinking different from you.
No, I don't know, but okay, what Lenin just said, we can find the diameter or the radius of the circle. How?
Well, the diameter of the circle should be the same diameter of the square. No?
No, we know the circumference.
The circle is not going to be,
Yeah, that's circumference. The circumference of the circle should be the same, like
yeah,
same
I would say that there is no picture like this, for example. We don't know if it's exactly this way.
Yeah, I was thinking about that, but I think it is not like that.
Okay, the perimeter of the square is 4a, and it should change into the circumference. Would it be accurate to say this way?
Yeah, that's what I meant to say.
So then what will be the radius of the circle then?
To a over pi.
And then let's compare the areas. The area of the square is a square, and the area of the circle, we have to say pi radius square. Yeah, is it correct? I'm not making mistakes here.
Yeah.
Yes? So then the square initially it was just a square. It was just a square. Okay, too many squares. The resultant circle would be pi radius square, and this is radius. Okay, if I simplify it, I get 4 over pi square. 1 pi will go away. 4 over pi. So what can you say? The area is increasing or decreasing then?
Increasing.
Increasing. By the way, you may not know this, but circle is a shape which has a maximum possible area at given circumference. It's a definition of the circle. There are no more 2D figures which have a higher area at the same perimeter. Okay, so if area is increasing, then I have more crosses. My induced field should be out of the page. So the induced EMF would be counterclockwise, yes?
Yeah.
Counterclockwise. This way. Let's find the EMF then. the transformation happened in 2 seconds. The magnetic field is 2 Tesla. So then induced EMF would be negative the flux final minus flux initial over the time. Negative sign is just the direction, so we already decide that the direction will be counterclockwise. So the final flux is a magnetic field multiplied by area of the circle. Initial flux, the magnetic field multiplied by area of the square. And this is the time. So we have 4 over pi minus 1 a square b over delta t. I don't know. This would be my equation to I would start working on. So area of the circle has coefficient 4 over pi. Area of the square is 1. You have to take difference because you change them. And then you divide it by the time. Time was 2 seconds, I guess. Magnetic field is 2 Tesla. And the size, I forget what was the size, sorry. 2 centimeters. Everything is 2. Why? I don't know. But we can try. Four over pi minus 1, 0.02 square, magnetic field 2 Tesla, time 2 seconds, goes away. I'm gonna get 10 to negative 4 as minimum. So we are talking about small values. And then 4 multiplied by these brackets. I would still say 1.3 or something like this, but you can tell me more accurate. Well,
At 1.09.
I'm sorry, it was hard to hear you. 1.2,
I got 1.09.
1.209, 1.21. Yeah, 1.2,
1.1.
1.1. Can
I
I
get
have,
the same.
yeah? Again, I would not pay much attention to the negative sign because this is the direction, and we know the direction is counterclockwise, yeah? If I want to do the same, but I'm gonna reshape C.2, all the same. But I'm gonna reshape 2-turn circular loop to 1 turn or vice versa. So let's say 1 turn circular loop. Well, we can say 1 turn square loop. I'm gonna change to 2-turn circular loop. Something like this. You have a square and you reshape it into two turns. what would you do in this case?
Wouldn't it be the same, just multiply by 2 because you multiply by n?
Okay, let's find the radius of this loop. How would you change the equation? So the circumference
But
is
Now
4a.
is 4a equals to 2 times 2 pi r. So r is going to be like a over pi.
Then when you find the initial flux, you would say magnetic field multiplied by area. Yeah. But when you go to the final flux, you have to use number of turns, magnetic field and area.
But I have a question.
Yeah.
Shouldn't shouldn't it have like two different R?
No, I assume that you have the loop of the same radius, but two turns.
Ah, okay.
How I draw this, it's it's just
Okay,
a way how I draw this. Yeah.
Okay, no problem.
So for the final flux, I would use number of turns because now you have two turns. They're smaller, of course, but they're two of them. So in this case, I would say two turns, magnetic field, and this pi new radius. So I would get 2 over pi b a squared. So you see it's a difference. And the result actually is opposite. We decrease area. Even if I multiply it by 2, because there are two terms. But because radius become too small, this factor 2 cannot compensate it. So this 2 over pi less than 1. So you decrease. And then you can find the induced EMF using the same equation, the final flux minus initial over time. But you have to include the number of turns here. Okay, we have time for one more or two more examples, and we are good for today. So we are talking about different way how we can change the flux. We can change magnetic field, the strength. We can change area, and that was example when you change the shape. Even if you can change number of turns. It's not a continuous kind of procedure, but still you can do this. There is another very good example how you can change area. This is like very famous. Every textbook has this example. And I'm sure I'm going to put this on the homework and maybe even on the test. It's so nice. So let's say you have magnetic field. Let's say out of the page just for fun. Magnetic field is constant, it's given to us, let's say 0.3 Tesla. So it's constant. And now the loop. The loop will be strange. You would have a piece of resistance here. Resistance. And you will have tracks, very long tracks. The distance between tracks is given. Let's call this parameter A. So right now, it's not even a loop, yes, because it's not a closed loop. It's just two tracks connected by a wire with a resistance R. I'm gonna have a moving part of this loop, like a bar here, metallic bar. And this bar can connect the top and the bottom tracks. So now you form a loop. Can you see this? And I will take this bar and I will move it by myself, by my hands, at constant speed. So either to the left or to the right. V. So let's say I'm going to move it at 10 meters per second. The resistance is 100 ohm. The magnetic field is 0.3. Parameter A, I'll tell you that parameter A shouldn't matter, or it should. Okay, maybe it should. 10 centimeters. The parameter B is a distance between the resistance and the bar. It's pointless to give you this parameter B because it's changing. Yeah. Parameter B
Yeah.
will be a function of time because it's moving. I can give you the number like 5 centimeters. It makes no sense. But let's discuss what's going on. You take this bar by your hand and you move it at constant speed to the right. What will be the direction of the current and what will be the current in this circular loop? What will be the force on the bar? Find current in the loop. Find the force on the moving bar. So in this case, when you take this bar and you move it by your hand, do you change the flux of the fields through the loop or not?
You increase the area.
We increase the area. We don't reshape. Well, in a sense, we reshape, yeah, but the circumference is not fixed. You increase the area, yes. What will be the direction of the induced current or induced EMF? What's going on? What is the change in the flux? What happens?
It's increasing.
We get more and more dots of this
Yeah.
green field. Then how are you going to fight with this?
There's going to be a magnetic field induced in.
Yes. This is your induced field. Then what should be the direction of the current or direction of the induced EMF?
It should be clockwise.
Clockwise. So this induced EMF will produce me the current. I'm going to check it with the right hand rule, number 3. Yeah. Okay, let's find it. So my induced EMF is a derivatives over time from area multiplied by magnetic field. For the area, now try to follow me because I'll try to derive you a nice equation. Let's forget about sign because sign is just a direction. I don't want to care about sign. So there's a magnitude. So area, if you agree with me, would be parameter A multiplied by parameter B. Yes?
Yes.
Parameter A is constant. The magnetic field is constant. The only derivatives I have to take from is the distance from the bar to the resistance, which is increasing. So I can say A small b over dt and the magnetic field. But what is the meaning of this guy? It's a rate at which we change distance. What is this?
Velocity.
Velocity, yeah?
Yeah.
It's a velocity. Do I know velocity? Yeah. So then we have this vertical size, vertical magnetic field, vertical size, and the velocity. Nice. I have everything. I have velocity, I have vertical size, I have magnetic field. I don't have what I don't have. The horizontal size, but I don't care about this horizontal size. And this is the induced magnetic field is going to be clockwise, yeah, clockwise. Yeah, clockwise. Parameter A is 10 centimeters, magnetic field is 0.3 Tesla, the speed is 10 meters per second. So, okay. So the magnitude of the induced EMF will be 0.3 Tesla, parameter A 0.1 meter and 10 meters per second. So I'm gonna get, I guess, 0.3 volt. Clockwise. Can I find the current? What would be the current then?
Multiply by resistance.
Oi, multiply by resistance. EMF divide by the resistance, yes?
Yeah, divide.
Like this. Ohm's law. So the value of the current, of course, depends on the properties of this loop. So we have 0.3 over 100 ohm. So I get 3 milliamp, yeah, clockwise. Nice, we answered the first question. The current will be 3 milliamp clockwise. Questions? How would you find the force on this bar? The magnetic force, not force produced by you. I would say because you move this at constant velocity, the net force should be 0. There is no acceleration. You have to apply certain force to compensate the magnetic force. What will be the direction of this magnetic force and what will be the magnitude of the magnetic force? Let's talk about the direction. The current is down, magnetic field is out of the page.
Will be to the left.
My gosh. It's to the left, yeah? Yeah? So this is a magnetic force. So we can draw this as a magnetic force, FB. And then you have to apply external force. It's your force, F external, to move this at constant velocity. Otherwise, it will slow down. So this magnetic force, we will try to slow. It's a friction, yeah? Remember, it's a friction force. The magnetic force, we will try to stop it. And if you don't want it to stop, you have to move it. So you apply your force. So your force should be exactly equal to the magnetic force. because velocity is constant. Can we find this magnetic force or external force in this case? If you have a wire with current inside magnetic field, the force was magnetic field, current, and the length. Am I right or I forget it? That is the force on a current.
And like that.
It's magnetic field, current, and the length. Current is 0.3 milliamp. The field is 0.3 Tesla, and the length is 0.1 meter. It's not 0.8, it's 3 milliamp, yeah? Three milliamp current, 0.3 Tesla, 0.1 meters is the length. Yeah. I'm gonna get some small values for the force. 0.9, 0.09 millinewtons. So we're talking about micronewtons. So basically, I don't know, 0.9, 10 to negative 4 newtons. So it's not very large force, yeah? But I have to apply the same amount of force to compensate this magnetic force to let it move at constant speed. So we got it. So this is answer number 1 or number 2, and that was answer number 1. Questions? It's cool, yeah? I have one more question. Probably we can just continue the same problem. If you have current through the resistance, then you have power consumed by the resistor, yes? Can we calculate power in the resistance? So the power, the energy per unit of time, per unit of second, consumed by the resistor. What equation would you use? Current square multiplied by resistance, or current multiplied by EMF, or EMF square over resistance, yeah? So anything like this may work. The current is 3 milliampere and the voltage was 0.3 volt, yeah? How much power is consumed by the resistor? 0.9 milliwatt. Is it? So it's close to 1 milliwatt. Now a question. The energy consumed by the resistor should came from somewhere. You consume 1 millijoule every second, yeah? Almost 1 millijoule every second. This energy came from where? What is the source of the energy?
The EMF?
But who creates EMF?
The magnetic field.
Yeah,
For the force that you give it.
Lenin, your answers all correct, but I can barely hear you.
Yeah. Yeah, it changes from the force that you give it.
The energy produced by me, by force done by me, I do some positive work. For me, is it hard or easy to move this bar? It's hard. Yeah, I have to
Yeah.
compensate this magnetic force. So I apply my force and I make it move. Lenin is absolutely right. I do some positive work. If you don't remember, the power produced by force can be calculated as a force multiplied by velocity. Because in reality, you can say the amount of work you do, force multiplied by displacement, and then you divide it by time. It's a work done by this force over the time. So then force times velocity. I'm sure you remember this, or maybe we just discussed it in physics 1, maybe you forget, but this is the amount of energy per unit of time I generate, or amount of work I produce when I apply force and the object is moving at some velocity. This is what consumed by the resistor, and this is what I produce. What was the force, by the way? 0.9 10 to minus 4 newtons, and velocity was?
Was 10 meters per second.
So if you multiply them, you'll get 0.9 10 to minus 3 watts, yeah? Look at this. It's perfect. This is what I would call energy conservation law. We have magnetic friction basically when you move this the bar, either to the left or to the right, it doesn't matter. There will be magnetic friction. And when you move this, you apply your external force, you do some work. And because you start to have EMF, and the EMF will make a current going in this loop, the current through the resistance will produce you some heat. So when you do this, when you move this, it will be hard for you because you actually produce the current and you produce the heat in the resistance. This is already like generator. Maybe it's not very effective form, shape, construction of a generator, but this is generator. You convert mechanical energy, mechanical work to electricity. If it's a light bulb, the light bulb may be flashing. You have to move fast enough probably to produce, but 0.3 volt is not that small. We have to say the magnetic field is too strong and you move this a little bit too fast. But yeah. Okay, that was one more example. How can you change the area and generate EMF or current? It's a different from previous example when you just reshaped your loop. You actually change the area directly in this case. There is another problem. Let me take one more couple minutes and then we are done for today. Which is based on this form, on this on this example. And this one would be maybe on your homework. And I like it personally because it's a cool problem. This problem inside this Savchenko book, fancy, nice book. So the problem is like this. You have resistance and you have vertical tracks like before. It's not a big deal. And you have gravity field, G, and you have magnetic fields. In or out, it doesn't matter. Because the magnetic friction force will be always against the motion. So it doesn't really matter the direction of the magnetic field. So you have external magnetic field and you have gravitational field. Magnetic field is perpendicular to the loop. So you have resistance, of course. You have magnetic field, you have gravity, and of course you have this bar which creates a loop. And now I'm going to give you mass m for this bar. What's going to happen? You let this bar go like a free fall motion. The bar will start to free fall down. But the faster it falls, let's say you have also the size of this L. The faster the bar falls down, the stronger EMF you produce. Remember, your EMF is magnetic field, the size of the bar, and the velocity. The only problem is that your velocity may change this time because it's a free fall.
Yeah.
When
So
it's
it
a
will-
free fall, it's increased. Yeah. Yes.
It will reach a point where the bar won't move anymore.
No,
Right.
no. Yes, but not. Yeah, I'm gonna explain. The faster you fall down, because of the gravity, you will start to fall down. The faster you fall down, the stronger EMF and the stronger current. That means the stronger magnetic force on this. If I write down forces, you have magnetic force, and you have gravity force, mg. The gravity force is always constant, no matter what, it's mg, yes. But magnetic force is getting stronger, stronger, and stronger. When they will be equal, it's not going to stop, as you say. The acceleration will be zero. They're going to stop accelerating.
Oh, okay.
It will continue to fall at constant speed. This is called terminal velocity. When people jump with a parachute, initially you have just gravity force and you're in free fall. But the faster you fall, the more air resistance force you have. And then eventually your gravity force and this friction force will balance out each other. And you will start fall down, move down at constant velocity. This is called terminal velocity. It's a constant velocity you will reach after a long time. So in this case, it's very similar. You have gravity, the weight, and you have the friction. But the nature of this friction force is different. It's a magnetic friction force. So eventually, when they balance out each other, the bar is not going to stop, because if it stops, there will be no magnetic force. No, it will stop accelerating. The problem could be find terminal velocity. Terminal velocity. Or you can say maximum velocity. The bar cannot accelerate more to faster speed than this one. What you're gonna do? You write EMF, and this is BLV. You can write current, so you take BLV divided by the resistance. You plug this current into magnetic force. So you take current multiplied by magnetic field multiplied by the length, and you make it equal to the gravity force. So the terminal velocity will correspond to a situation when acceleration will be zero, or magnetic force will be equal to the gravity force. So the bar is not accelerating anymore. It will reach the maximum possible speed, velocity. And this is what we call terminal velocity. Yeah. It's a very nice problem. It's very cool. In terms of, it's basically the same what we did here, but it's a nice analogy with the free fall and air drag force of a parachute. But this is magnetic friction. Okay, I believe it was a very good class, at least for me. I enjoyed this Faraday's law. I try to open new homework with the problems which are related to this Faraday's law. Maybe if you have time, you can take a look. Thank you, guys, and I'll see you on Monday.
Thank you,
Good, Professor. Have a nice day.
Enjoy the weekend, everyone.
Yeah, you too.
Thank you, Professor.
Thank you.